All right, hello everyone. Welcome to 61C lecture. I'm Shreyas. Some of you might know me. Professor Asanovic is. Thank you. Oh, thank you. Professor Asanovic is out today. He had a little personal emergency, so I'm just filling in for him for today. Today we're going to continue talking about the single-cycle CPU data path where we left off last week, and we're going to move on to talking a little bit more about the control, a little more concretely. So here we have the 5 steps of processor design that we followed through last lecture. Right? We went through steps 1 through 3, where we looked at all the instructions that we have. We figured out what they mean. We figured out what registers we're dealing with, where data is flowing from which register to memory, from maybe a register to another register. We looked at all these things, and we figured out what data path components we needed. And we assembled all of them so that the data could flow in the way that we analyzed in step 1. Today we're going to be looking at these last 2 steps. We're going to look at the implementation of each instruction to figure out actually how every single piece of data is going to flow through this data path that we've already created. And when we do this, we'll realize that there will be a lot of different points in our data path where we have to make decisions based on what instruction we're dealing with, whether we're writing to memory or not, which register we're writing to. And so based on these decision points, we're going to figure out the control logic values of the signals that determine these decision points. So one quick aside before we get started with that. Notice that we're going to be working with a single cycle CPU. We looked at this last week. The idea with this is basically, for instance, if we have an add or a sub instruction, the entirety of the addition or subtraction will happen within one whole clock cycle. So from this rising edge right here, I'm just going to use my mouse pointer for the benefit of those who are just watching the webcast. So from this one rising edge to the next rising edge is the entirety of the amount of time we have to finish executing the instruction. So when we begin, first we grab the instruction by using PC. As soon as we've done that, after some clock to queue delay, right, now my PC has some new value. Once I've got the instruction, it'll take some amount of, once I know my PC and I go to memory, it'll take some amount of time for me to actually get the instruction that I want to execute. So that's the instruction memory access time. Once we have that, we have this new instruction. Now we can start to decode this, right? We can break it up into a RS, RT, RD, op, and func little bits. This example, we're looking just at add and sub, so we know these are the fields we're looking at. Once we've looked at all these values, we'll put it through some control logic. And that time delay, the delay through control logic, that bit is something that we'll talk a little more in depth about today. But in that amount of time, we're going to take these different fields that we've got from the instruction, and we'll figure out how to set up our data path to execute that instruction. Once we've figured that all out, we can give that to the ALU and the reg file. Right? We talked about the reg file last time. It has these 3 RD, RS, RT inputs and some other control inputs. It's basically sort of a generalization over the 32 registers that you have. It's an API for you to be able to access all of those. Once we have those, we can address the registers that we care about. We can set up the ALU right here to do addition or subtraction. Once that's done, it'll take some amount of time again, right? Some combinational logic delay for our values to get through the ALU and give us the result. And then once we have that result, after some delay, once we have that result, we're going to write it to our registers right here. So in this process, there are these 2 control signals, this ALU control and this reg write value. These are the 2 control signals that we needed to use in order for our data path to work correctly. Right? The reg file, we said, is this generalized 32 register box. Now we need to tell this box, okay, I want to write to a particular register. So that reg write value needs to be a 1, signaling that I'm going to do a write. So our control logic needs to set that signal to a 1. Similarly, ALU control needs to be set so that this ALU will do the right thing, whether we want to do an addition or a subtraction. That ALU control line, that one won't be just 1 bit, right? This ALU is able to do multiple things. So this ALU control line needs to be able to represent a whole bunch of different instructions. So that's what will be on that line, and that will set up the ALU to do the right thing. So as we said in this list of 5 steps, we're going to go through step 4 right now. We're going to look at a few different instructions, and we're going to see what parts of the data path it interacts with and where we need to make decisions along the data path and set control points appropriately. So we looked at add and sub. In add and sub, we had to set reg write to a 1 and ALU control to add or to sub in the ALU. Now, if we're looking at the logical OR with immediate instruction, ORI, right? The way ORI works is it has 2 registers and an immediate field. So what do we have to do here? We're going to go to the reg file, right, to read some value. And that value that we're going to read is specified by RS. So we have RS going into RA. So since RS is going to RA, on bus A, we're going to get the value stored in the register specified by RS, right? So far, so good. No control logic required. This will go into the ALU. And then the other value that we want going into the ALU is no longer the value from bus B, right? With the add or the sub, we were taking the value from bus B and putting that into the ALU. We don't want that value anymore. We want to put the immediate into the ALU now. So we're going to have to introduce this mux here that chooses between the value on bus B and the value provided to us by the immediate field. And we're going to want to extend that immediate field first before we feed it into the ALU. The ALU expects 2 32-bit values, right? So we'll take that immediate, that 16-bit immediate, and we know from how ORI is specified that that immediate needs to be 0 extended. So once we 0 extend that immediate right through this box, we're going to put it into this mux, and now we're going to have to introduce a control signal that lets us choose between the register value on bus B and this 0 extended immediate value right down here. So here we've introduced a new control signal called ALU source, and in this case we will set ALU source to a 1 so that we're getting the immediate value rather than the register value. The other control signal that you've already seen is reg write. That one has to be a 1 because we're going to write to the register specified by RT. But notice now that this is slightly different from the add instruction where we're writing to RT, not RD. Here we were writing to RD. The read-write port of that reg file is taking RD as an input. But for I-types, we don't have an RD. We need to write to RT. So now we're again going to have to introduce another mux, because sometimes we want RD and sometimes we want RT. And we want our data path to be able to do both. So we put this mux here, and we're going to have to introduce another control signal that chooses between RD and RT to be specified in read-write, on the read-write port. The only thing is here, RT is still going into the RB port. And we're still reading the value at RT. Is that a problem? So since RT is going into this RB port, we're reading the value specified by RT in this reg file, and it's getting output at this bus B wire. But it doesn't matter, because this mux right here will choose the 0 extended immediate and not this bus B value. So in this case, it doesn't really matter what we're reading from the reg file at RB, because we're going to ignore it completely. So this data path, since we made it so that it can support all instructions, it will sometimes happen that some of these wires in our data path are accessing values or have values that we don't actually care about. But we just have this so that we can use this same data path for other instructions. So that's ORI. Let's take a look at some more, right? So we looked at an I-type and we looked at an R-type, add and ORI. Now let's talk about load word. So this is an I-type also, but now this one has to interact with memory, right? So when we're looking at the load word instruction, similarly we have RS, RT, and the immediate. So similarly, just like before, we're going to use the same machinery that we set up for the previous I-type, right? We have the immediate, we're going to want to extend it probably. We're going to want to choose between these two values, and we're going to be writing to a register. And we no longer have an RD, so we'll definitely be using this mux. For load word, though, we need to introduce a few more things, right? First of all, we're going to be interacting with data memory. And instead of 0 extending, since this is a load word, this immediate, right, gets sign extended and then added to the register value. So instead of this being just a 0 extender, now we're going to have to replace that with a generic extender, which can either sign extend or 0 extend. Now, so when we do this, anytime we do something like this where we introduce a decision point in our circuit, in our data path, we're going to have to put in a control signal. So that's where this ext op comes in. So we're going to have to specify to the extender whether we're doing a 0 extension or a sign extension. In this case, we'll do sign extension. Let's see, what else is new here? Mem to reg, this mux is new, right? Since we added a mux, now there are two choices. Since there are choices, new control signal, and we're going to call this control signal mem to reg. What this multiplexer, what this does is it chooses between the output value of the ALU and the output value of data memory. In the case of load word, when we're going back to the register file to write over here, in the case of load word, we want to take the value output from data memory. Right? We specified some address to this data memory that was calculated in the ALU. We fed that to data memory, and that gave us some output value. And it's this output value that we want to store into the reg file, not the value calculated by the ALU. So we have this mux, which chooses between those two values. And in the case of load word, we're going to take the data memory value and put it into the reg file. What's the value that the ALU is outputting in this case? The final address from which we're loading, right? So for load word, bus A will contain the base address, right? The one that's specified by RS. That will be on bus A. And then the other input to the ALU, we're going to set ALU source to select the sign extended immediate. And then the ALU control will specify that the ALU should be doing addition. So we're adding together the sign extended immediate and the value stored in that base register, giving us the final address from which we're going to load. Once we load, now we have to choose between the loaded value or the address. And of course, we want to store the loaded value, right? That was the whole point of this instruction, to get some value from memory and put it into a register. So that's what we do here. Now, there's also the store word instruction. Oh, let me go back. Yeah, there was a question back there?
Yeah, so why do we in our registration destination we choose RD instead of RT?
When would we choose RD instead of RT?
Or are we choosing RD to write memory into, or am I reading the mux?
So this reg dest right here, it will have to be 0. We don't have an RD value at all in the case of an I-type. So whenever we have an I-type, reg dest will always point to RT. We need reg dest to be a 1 for the case we looked at here. For this simplified version, we were just assuming we're just going to put RD into this write port. But sometimes we want RT. So we introduce this mux here. Now that we've introduced this mux, RD will have to go through this mux for add. So whenever we have an R-type, for instance, add, that's when reg dest will be a 1. Sound good? Okay. Let me actually take a moment. Are there any other questions at this point? Yeah.
Are all these functions designed to take a certain amount of time? They will all complete within one clock cycle? Or?
Okay, so the question was, do these instructions all take about the same amount of time? Are they designed to fit in one clock cycle? So that's a really good question. What do you think? We will need to have all of these complete in the same amount of time, right? When we give any system, any sort of synchronous digital system, whether it's our CPU or any other sort of circuitry, we have one fixed clock, right? And we can't vary the clock period. So we'll have to supply a clock such that all our instructions can finish in that one clock cycle, right? So how long does the clock period have to be then? As long as the longest instruction. It needs to be able to accommodate the longest time-taking instruction. Yeah, back there.
Is that really inefficient because things that access memory would be much slower than arithmetic operations?
It is, yeah. So the question was, isn't that really inefficient? We're waiting, for instance, for the longest running operations, which we know are going to be the load word and store word because they're accessing memory, right? If you remember that Jim Gray model of memory accesses, we're going to Pluto, right? Whereas when we're just dealing with registers, those are much quicker. So isn't this really, really inefficient? And the answer is yes. We're wasting a lot of time for all the for the R types and the I types that don't deal with memory. We're wasting a lot of time. How can we do better? Keep that question in the back of your mind. We'll get to it in the coming few days. I won't answer that now. Yeah?
So as long as your operation finishes before the clock cycle, it's like your state will be held until the next one, right? That's how it works.
Right. So the question was, as long as your operation finishes by the end of the clock cycle, your state will be held? Yeah, so basically when you're designing your CPU, you design your CPU first and then you choose your clock cycle frequency, your clock frequency. So once you've designed your entire data path, you set up your control signals, everything, that's when you choose your clock frequency. And when you're choosing the clock frequency, you better choose a clock frequency such that the longest running instructions can finish by the end of that clock period. There might be some instructions, and we know there will be, that'll finish much sooner. And that's perfectly fine, as long as they don't run over the end. Because if they run over the end, now your next instruction is executing before the previous one finished. And that will lead to inconsistent state. Any other questions? So far, so good? Yeah.
So what is all of this actually writing the output
What part of this is doing? So the question was, what part of this whole data path is actually doing a write?
Yeah.
So this reg file, we looked at this last week briefly. This reg file, this box is sort of we're just giving you this black box, and we're telling you this contains the 32 registers, and we're giving you a few inputs, and just use those to write it. The actual writing and reading, all those operations are happening inside that box right there. You're given these 3 ports, the read-write, the R-write, and the RA and the RB ports. These are 5-bit inputs, where you specify, in RW, you put in the register number to which you want to write. Once you've specified that, and regwrite, this control input, if that's a 1, then whatever's on bus W, the write bus, will get written. That data will get written, that 32-bit data will get written to the register specified by RW. And RA and RB specify where you want to read from. And that's what will be on bus A and bus B. The values read from RA and RB. In this picture, what we're saying is we're always going to feed RS into RA and the value of RT into RB. So essentially at bus A and bus B, we have R of RS and R of RT. Okay. Yeah? What's that little thing under data memory? Right here. I think that's my slides being funky. Let me check.
Like memory.
Oh, yeah, that's the Y from data memory running over at the end. Sorry about that. I just got these slides this morning from Professor Asanovic, and they're a little funky. Pardon me for that. When the slides get put up on the website, it'll be a little more clear. That's just a Y from data memory. Good question, though. Okay. So I'm going to move on to store word. We're going to take a look at this one. So store word is going to be probably the most involved, is definitely going to be the most involved instruction. Store word uses all the parts of our data path. We're reading from the registers, we're writing to the registers, we're doing some sort of ALU operation, we're dealing with immediates, and we're dealing with data memory. This is going to exercise our entire data path. So this will help us flesh out the final bits of our control logic. So the first thing we see is that regdest, we've talked about this. This will be set up, right, to write to RT, because we don't have an RD at all, right? So store word stores to RT. RS and RT are in here. We don't really care about bus B, because ALU source will choose the sign extended immediate. Right? We'll take the immediate, we'll set xop to sign extend. We'll feed that into this mux right here, and we'll set ALU source such that we're selecting this immediate. Once we have that sign extended immediate and the value in RS, we're going to set ALU control to be doing addition. Right? We're taking the base address and stored in the register specified in bus A, and we're adding on the sign extended immediate. Once we have those two values, that gives us the memory address to which we're going to write. So that's what this line right here, going to adder, will do. And now in data memory, before for a load word, right, this picture of data memory assumed that the only thing we're going to be ever doing with data memory is reading. Now we need to be able to write. So now we're going to need a write enable port, which will require us to have a memWrite control signal so that we can enable or disable this. Right when we're loading, that signal is going to be a 0 so that we don't overwrite data that we're reading by accident. We only want that to be a 1 whenever we're storing to memory. So that'll be a 1 in this case. And now we need some way to specify the data that we want to write. There's no way to do it right now in this data path. So we'll actually have to add a piece to our data path here. Where is the data that you want to write? RS, right? RT. It's stored in RT. Right? In store word, we take the value stored in RT and put it in RS. Right here, R of RT gets stored into memory. So now we need to get the value read from RT. Fortunately, we are always reading the value from RT, right? RB is always getting fed RT, so bus B always has the value read from register RT. So all we need to do is draw a little line from bus B to data in to get that value. Yeah?
I have a question. So for I instructions?
I types, yeah.
I-type instructions. Why is it OPRSRT instead of OPRSRT? If we use OPRSRT, then there is no need for the reg test must, right?
Let's see.
And the bus B can be, because bus B is useless anyway, because you're going to load the immediate anyway. Right?
So you're saying, why do we have an RT at all? Why is this not an RD?
Exactly.
And let's see.
That's RD, because RB is useless in all of the I instructions because you're loading immediate.
So the point is that why don't we just use RD, because we are always using RB anyway to get RT. Let's see. RT, why are we using that? That's a good question. Any thoughts on that?
So basically, it's because of it's determined by the designers of it. So, yeah.
That's just how the design was. That's how the system was just designed. Yeah. I'm not quite sure exactly what the engineering reasoning was behind that. That's a good question. Maybe post on Piazza. Let's see if someone else can chime in on that. I don't know the answer to that off the top of my head. Yeah. What exactly is a bus? That's a good question. A bus is just a bunch of wires. That's all it is. It's just a fancy way of saying a bunch of wires. So when I say bus A, I'm referring to this bundle of 32 wires. Right? When I don't say bus, when I'm just dealing with single wires, it's just a wire. Right? So this reg write signal, for instance, is just one value. So I just need one wire going in. For bus A, I have a 32-bit value. I can't put that all on one wire. I need 32 different values, right? So I'm just going to have a bundle of 32 wires. A bundle of wires is a bus, essentially. Yeah. Okay. Where was I? We just read from memory. So we've read from memory, and now we're just going to put things through this mem to reg register. Again, just as with load word, we want the value that we got from data memory, not ALU. Oh, sorry. Back up a second. Sorry. Store word. We're not doing anything we're not putting anything back into the registers. So this value from mem to reg what does it need to be? It doesn't matter. I don't care. Because whatever is coming out of the ALU or whatever is coming out of the data memory, I don't care about either of those values because I'm not going to write anything to the reg file at all. This reg write control signal is going to be a 0, which basically means that whatever's on bus W, I'm going to ignore. So then mem to reg, I don't care what that value is. I can just set it to whatever I want. It can be a 0 or a 1. So we're not going to specify exactly what that needs to be. Okay, let's see. Oh, okay, we forgot one last instruction, the branch instruction. This one's slightly different because now we need to think about how the PC plays into this whole data path picture, right? We haven't been talking about the PC at all in this picture right here. We need to talk about how the PC gets affected when we have, for instance, a branch instruction. So the way we get an instruction from memory is just by taking the value stored in the PC register. I haven't been showing you that PC register, but there is a PC register somewhere that contains the address of the current line of code that we want to execute. And we fetch that instruction from memory. In the case of a branch instruction, what we do is we read the value stored in the RS and RT registers. And if they're equal, then we know that we need to take the branch. If it's 0, we're not taking the branch. So we do this comparison, and we're going to call the result of that comparison equal. If equal is true, this is the new value of PC. Otherwise, we just set PC to PC plus 4. That's the normal operation, right? So the special case is when equal is true, and in that case what we do is we'll sign extend this immediate to get a full 32-bit value. And then we'll multiply that by 4, because as you all hopefully know, in the branch instruction, this immediate is an instruction offset, the number of instructions away we're trying to go. But PC stores a byte address. So we need to convert this into a byte offset so that we can then add it onto PC. So that's what we'll do here. So here is what we've come up with for the data path circuitry to be able to do that. Right? We have two possible conditions. That's what this if statement was telling us, right? In one case, we want PC plus 4. In the other case, we want PC plus 4 plus this offset. So that's what this mux right here will do. It'll choose between, so we have this PC register right here that stores the current address. That's going into this adder, where we're adding 4. So this mux's first option is PC plus 4. And the other option is this PC plus 4 plus somehow we're going to get the new PC offset and add it to PC plus 4. So those are the two options here. So npc select we'll have to introduce a new control signal that's able to choose between either one of these two ways to update PC. The one other slight modification we'll have to do is to be able to actually do this comparison. This R of RS equals R of RT. Right? Well, our ALU is set up perfectly to do this. It gets R of RS and R of RT. Notice that this is sort of the simplified version of the data path that we saw when we were looking at just add. So the slight modification that we're going to have to do is we're going to need this equals output coming out from the ALU, besides just the regular ALU output. That output is what we're going to use, along with the fact that we have a branch instruction, to choose how we update our PC. So essentially, our npc select is going to have to take into account two different factors, right? Whether or not we have a branch, and whether or not the equals operation succeeded. So one option could have been just to directly specify the mux somehow, using these two values. Or the other option is to take into account whether or not we have a branch or not a branch. So we're going to do that second option, because it turns out if we look at this truth table right here, right, if npc select is 0, which means that we're not going to be using a branch instruction, it doesn't really matter what the equals operation gave us. our mux is going to be 0 because we just want PC plus 4. If npc select is a 1, then whatever the comparison result is, that's what determines the mux. So this output column should look very familiar. What does that output column look like? This is a logic gate, right? Which one is this? It's just an AND. So all we need to do is AND together npc select, which will tell us basically whether we have a branch instruction or not a branch instruction. And the other input will be the result of that comparison. If both of those are true, then we want to choose PC plus 4 plus this PC extended. PC extend here stands for the times 4 and the sign extension result. That added to PC, and then this ANDing will tell us whether or not we want to take this sign extended plus PC plus 4 value. Any questions about this branch instruction? Okay. So if we step back for one moment and and see all these little bits that we've accrued together, this is the picture that we get. So I'm just going to leave it here for 30 seconds. Let's just bask in the glow of this beautiful data path. Oh, with all these funky letters. I'm so sorry about that. But this is going to be our full data path. This has all the little bits that we need for all of our instructions to work, along with all the points labeled where we have decisions to make. And those are highlighted in blue. Right? We have the reg file, we have the data memory, we have the ALU. Those are going to be sort of our three big blocks of functionality in our data path. And then we have a whole bunch of these little muxes and adders and sign extenders that basically give us the option to execute any MIPS instruction at all using just this one giant piece of circuitry. Any questions? Yeah.
The entire left part is only solely to determine whether it's a branch.
So the question was, is this whole thing on the left, is this just to figure out branch instructions? Well, for now, yes. But what else can modify your PC? Jump instructions. So this whole left side will also come into play when we want to implement J instructions. Right now, it's not set up to do any J instructions. We'll have to further modify this to be able to work with J instructions, right? This isn't actually the full data path. There's the full data path so far. But yes, all the circuitry on the left there with all these muxes, this is just to figure out the PC and to get the next instruction. Other questions? Yes. Okay, the question was, who sets npc select? That's a good question. Who sets any of these blue wires? These blue signal names? Who sets that? All of those need to be set to execute any particular instruction, right? So what do we think? How are we going to set those values? Yeah? Right, we're going to have to look at the opcode and the funct. The opcode and the funct tell us what instruction we're going to be executing. If the opcode is all 0, we know it's an R type, and then we'll look at the funct. For all other instructions, we're looking solely at the opcode. So based on the opcode and the funct, we're going to have to create some circuitry that figures out those values. We'll talk about how that circuitry works soon. Other questions? Okay. We're going to take a quick break. We're going to look at some pure instruction questions. So take out your clickers. If you're using iClicker Go, you're going to have to look for me. I'm not entirely certain how it shows up, but you're going to have to look for CS61C machine structures. The name that you usually look for, but then it's going to have underscore Shreyas appended onto the end. So look for that if that's what you're using. So once everyone's ready, we're going to do this. Basically, this question's asking you what pseudo instruction or instruction, which one of these instructions, right? We're giving you 4 different possible instructions. Of these 4, which one would not need any new Datapath hardware? So think about that. Don't talk to your neighbors yet. I'll give you a chance to do that in just a bit. So vote in. Plug in what you think the answer is, and then I'll give you a chance to talk to your neighbors to figure out the answer.
Alrighty.
All right, I'm going to stop this. And let's see if this cooperates. Okay, and let's take a look at what you all thought. Haha. So, wow. That's impressive. Okay, so when that kind of thing happens, that's totally a reflection on me. So we're going to talk about this. I'm still going to give you a chance to talk to your neighbors. So talk to the person next to you and see if we can narrow this down to maybe 2 options, and then we can talk about those options. But this is really impressive. This is almost, oh my God, perfect. All right, take 2 minutes, talk to the person next to you. I'll start the poll so you can vote in as you figure out what you need to do. And we'll talk about the answer in just a minute. right, let's take 30 more seconds and vote in. Put in your votes. There were 300 to begin with. Let's get to 300, and then we'll talk about the answer. Almost there. We need 304, or close to that at least. So vote in, see what you think. All right, and it's going away in 5 more seconds. Vote in if you haven't. 296, let's see if we can break 300. We did it, all right. 304, it was 304. 3 more people. Hey, all right, nice. Great. Let's see if we reach any kind of consensus here. We did not. Okay, so why don't we do this? We're going to start with the most popular option, C. Why do people think it's C? Someone want to talk to me about C? I mean, it's spread all across the board, so it doesn't matter. Just give me what you think about C. Yeah.
We didn't really talk about the offset, but we talked about like safe word. So
Okay, well, all right, let's take a look at option C, and let's see what it's doing. So option C is basically going to be a store word, but now you also want to increment the base address by the offset, right? So we know that we don't need to do any modifications for store word. Obviously, we went through store word and we put in all the bits of machinery that we needed to implement store word. So the new part is incrementing the base address by the offset. So the comment tells us that we want to increment the value stored in RS by the offset after the store. So RS incremented by offset, what is that value? So RS plus offset. Someone, I saw a hand up here.
the offset's that's the issue,
Right.
right?
What is RS plus the offset? It's the address. It's the address to which we're storing. So we have that value, right? So we don't need to add any more circuitry to compute that value. That value is right here at the output of the ALU. Now we just need to store it back to RS. So I need to set memreg to 0. I don't need to add any circuitry to do that, right? I just need to set memreg to 0. So far, so good. The value comes to the reg file. It's at bus W. I need to have reg write to set to a 1 now. Not a big deal. I can set it to 1. But I need to specify that I'm storing the value at RS. Can I do that right now? I can't. I'll have to extend this mux so that it has 3 options. RS, RT, and RD. And this regdes will have to choose between one of those 3. So C will require me to change this mux into a 3-input mux. So that's not quite the answer. Let's talk about D. That was the next most popular option. This one wants us to shift left logical by 1 bit. How would we shift left logical? I heard a reason here. There's nowhere here in this picture where we're dealing with shamped. We can't specify shift amount in here at all. So we'd have to modify the data path. Let's take a look at B. Add 2 registers and branch if result is 0. Can we do this one? Yes? People are saying yes? Let's see how we could do it. Add 2 registers. We can do the addition of 2 registers, right? We looked at add. That part we can do. We know that this data path is capable of doing a branch. There's circuitry for it right here. The thing is, now we want to branch if the result of comparing 2 registers, if the addition of 2 register values is a 0. Can we do that? Yeah.
You never ANDed NPC selected equal
We're going to say NPC select is the addition is the ANDing of equivalence. Okay, so let's say NPC select was what we actually needed to be. Can we do it then? It's not quite a BEQ, right? Because we're adding the value of two registers, and we're checking if the result of that addition is equal to 0. So turns out B is probably the closest thing to the right answer for this question. And I say the closest thing because I didn't really ever tell you what's inside the ALU. You don't know if the ALU is capable of doing this comparison. If the ALU can do this comparison, whatever's inside the ALU can do this comparison, then sure, I can do that. I don't need to do anything. Because really all I'm saying is that instead of the equals output of the ALU, instead of that being just a simple, are these two numbers equal? If I just say that that's going to be add these two numbers and check if it's equal to 0, then I can do that. Because I'm just taking the machinery for a branch that I already have, and I'm taking the machinery for the add, which I already have, and combining them. So B is going to be the closest thing to the right answer here. A, let me just go through A. Branch if register equals immediate. This one's going to be the second closest to the correct answer. I can do a branch if a register is, I can do a branch if two registers are equal, right? But if I want to compare a register to an immediate, my I-type, the ones that I use for branches, the I-type field, the immediate field is used for the instruction offset. If the register value that I'm comparing to, the value that I'm comparing the register value to, this immediate right here, if reg equals immediate, if this immediate happens to be the same exact value as the instruction offset to which I want to branch, then this works. So in that very narrow case, if the amount I want to branch by is the same as the value I want to compare to, then A works. Otherwise, A does not work. So this one's a little tricky. There are a lot of caveats in each of the answers, but we're going to say B is the correct answer here. Because that one I can do without any external modifications to the data path. I just need to make sure my ALU is capable of doing that operation. Yeah, questions? Can this data path do add immediate? I believe it can. I would set my xstop to sign extend my immediate. I would set ALU source to grab that immediate, and I would add that with RS. And that would give me the correct addition value.
A would work because then in the ALU after you have the immediate and the thing, it can see if they're equal the same way and do a normal branch. But I don't know what I'm missing.
Yeah, exactly. It can do that. This circuit can do that comparison and then give you that equals value. But the thing is, if this immediate value is different from the immediate by which we want to branch, then we can't do this. Because then we're dealing with two different immediate values. The amount by which we want to branch and the immediate against which we want to compare. Since there'd be two different immediates there. If those immediate values happen to be the same, then my regular old BEQ can encode all the information I need, and this would work. Let's see. 2 more questions? Okay, let's take them.
For D, could we just multiply it by 2? Like I was kind of assuming maybe that's part of the ALU.
We don't have a shamped at all here. We're not able to specify a specific immediate value here at all. We'd have to somehow introduce a wire that says 1. Yeah. Can the ALU do multiple instructions in one clock cycle? The ALU is not a synchronous device. Notice that it doesn't take a clock. So as soon as you put values on bus A and bus B, it starts chugging away. After some combinational logic delay, it'll have an output. There's no sort of sense of timing on the ALU. So in that sense, yes, it could do multiple instructions within one clock cycle, but there'd be no way for you to figure out when those things would finish happening. So you can't really do multiple things in the ALU in one clock cycle in such a way that you can use both output values. What was that? Yeah, you can do that with one ALU operation, right? You just subtract them. You can use subtraction to figure out if the addition will end up being 0. We're going to keep moving in the interest of time. If you have more questions about this, we can talk at the end of class. So I just have some administrivia. Midterm grades will be out soon. Hang tight for those. Assignments due. Homework 4 is due on Sunday. Keep that in mind. Hopefully, it's not too heavy. It should be manageable, hopefully. It's just synchronous digital systems. I will take those boos into account, but I don't make the rules. Project 1-2 is due on Thursday. That's the big one. So if there are boos for that, I will hear them on the next slide. How are you all doing with Project 1-2? So vote in. If you haven't started, but that's A. E is finished, and everywhere in between. So vote in. Let's see if we can get to 304. Vote in. Let's hit 304, or 306, I think it was. Okay, and I'm closing the poll in 5, 4, 3. Oh, come on. Almost there. Okay, I'm going to cut it off at 45. And, okay, we're going to stop that. Okay. Let's see, do we want to see how everyone's doing? Let's take a look. All right. Hopefully you all will get started as soon as lecture finishes, because it is due on Thursday. So get cracking. All right. Let's move on to this nice little picture. Okay. So this was the data path that we've been looking at. And now let's talk about the actual values, right? We've been sort of mostly focusing on the data path and where those decision points will be, pinpointing those decision points, right? Everywhere we introduced a mux, that was a decision point. The NPC select and equals, now it's corrected. The reg right, the reg dest, all these underlined values are all your decision points. So now let's start talking about what these decision point values actually need to be. The x stop, that needs to be able to specify whether we're zero extending or sign extending, right? It's just two possible values, so really it's just one bit. We can choose how we encode that. We can say arbitrarily that zero extension will be 0, sign extension will be a 1. So we can figure out the x stop value. And so those are the values that we'll need there. Memwrite needs to be, where is memwrite? Memwrite is right here. This needs to be a 1 whenever we're writing to memory. So that's just your store word instruction. Or if we were to flesh this out more to be a full MIPS processor, then we would also need that to be a 1 for store byte and store half. Then we have ALU source. ALU source chooses between the immediate or whatever's on bus B. Again, a 1-bit value, right? Because we just have these two options. Then we have mem2reg. Again, just a 1-bit value. This chooses what value we'll write to the reg file, whether we're writing the output of the ALU or the output of data memory. So it'll really just be a 1 whenever we're doing a load word, or a load byte, or a load half. Then we have ALU control. The ALU control is different from all of these other signals because it's actually going to be more than one single bit. We need to be able to specify all the possible operations that our ALU is capable of performing. We need to be able to say add, sub, or, XOR, and, all of those instructions. So ALU control is going to be as wide as log base 2 of the number of operations my ALU supports. I need to be able to choose any of the possible operations that my ALU supports. So ALU control will be just as wide as it needs to be able to address any one of those. And we can call the value on that signal add or sub or. These will, at the end of the day, be encoded in some sort of binary encoding. But we can just give them names for now, and we can just say, well, when we're doing add, the add instruction, ALU control will be add. So the question came up before, how do we set these values? So the way we set these values is by taking into account all of these different portions of my instruction. When I read the instruction from instruction memory, I will look at the opcode. The opcode will be the very first thing I look at, right? Because that will tell me what how these other instruction format chunks break up, which ones I care about. I'll always be reading all of these bits, right? It's not like I won't read some of these bits for some instructions. I'll always be reading all of these bits. But inside this control box, excuse me, here I'll have to take a look at the value of op to figure out how to set each of these control signal values. So when we have the add instruction, for instance, we know we'll always want to be fetching the instruction from memory. And then the actual operation that we're performing is right here. We're adding together the RS and RT values and storing them in RD. And then we're incrementing PC by 4. So if we look at the very first thing that this instruction does, which is fetching the instruction from memory, this is what we're looking at. The instruction fetch unit at the beginning of add is going to be exactly the same as the instruction fetch unit for all our instructions. We're always going to go to memory, to the address specified in memory by PC, and get the instruction from there. This portion will never change. There are no control signals for this portion. Right? We're always getting instruction from PC. Now we move to the actual functional part of the add instruction. And the red lines sort of specify the relevant parts of the data path that are active for us at this time. Here we have RD, RS, and RT specified. Right? So we want RD to be going into the reg file. So regdest is going to be equal to a 1. We know that once we've computed the result, we're going to want to write it. So regwrite is going to be equal to a 1. Actually, let me see if, oh, look at that. I have nice little highlights. Okay, so we'll actually follow this order. ALU source, that's going to need to specify 0, going to be 0, so that we get the value on bus B, right? And that's going to be the value we're reading from RT, R of RT. ALU source chooses that guy right here, so that's the one that goes to ALU. Xstop, this control signal, we don't care what it is. That will never make it through to the ALU or anywhere else for that matter. Since this is not one of these highlighted red lines, I don't care what the Xstop value is, so I just put an X there. When I design my actual control unit, which sets the values of all these, I don't actually care what it is, so I'll leave it to be a don't care, and I'll just choose whatever value makes my circuit the most convenient. So I'll just say X for now. The ALU control will have to specify that we're doing an add instruction, right? Memwrite is going to be a 0. We're not doing a store word instruction. That's the only one where this will be a 1. For now, it's 0. Mem to reg, this better be a 0, because where you want the value that the ALU is outputting to come out of the ALU and around and back to the reg file. Since that's coming to the reg file, we already talked about this, regwrite will be a 1, and I want to write to RD, so regdest will be a 1. And npc select this signal. We're going to call it npc select. We call this npc select in the beginning, and this was just meant to be whether or not it's a branch instruction. From here on out, whenever you see npc select, that signal is a signal that tells us how we update the PC. So in this case, we're going to update it to be +4 from the previous PC. So this picture now gives you all the values of all the control signals of add. So this control box that we looked at, now this will just contain some and not and or logic that will combine these values to set each of these control signals to be exactly what's specified on this picture. So I just need to look at the opcode and the funct, and based on that, I just need to set each of these values. So if I think about that, really all it comes down to is it's just going to be one large truth table, where the input is going to be the opcode, the funct, RS, RT, RD, the immediate, and so on. And the outputs are going to be all of these different signals. And we've already talked about how to go from a truth table to Boolean algebra and then to a circuit. So that's really all we're going to do. So for the rest of this lecture, I'm just going to walk through a few more instructions and figure out what these values will be. Excuse me. Oh, and this is the last part of the add instruction where I'm doing PC plus 4. So this will be the same for all the instructions except for my branches and my jumps, because all I'm doing is setting npc select such that this mux does PC plus 4. Ooh, excuse me. Okay. This is a big gnarly one. This is a jump. There's a lot happening here. Let's see if we can take this one step at a time. The jump instruction. Will we be doing anything with the reg file? No. There's nothing that we need to do with the reg file. The J instruction format doesn't even specify any registers, right? So I won't be doing anything here. What about data memory? Again, no, we're not dealing with memory at all. The ALU, similarly, I don't need to do anything here. The J-type instruction, all it does is it updates the next PC. So each of these xstop, ALU source, ALU control, regdist, all of these, I don't really care what the values are, as long as I set these critical values, the memwrite and the regwrite, to a 0. As long as these two values are a 0, nothing gets modified in my reg file or memory. If nothing's getting modified there, I'm essentially doing nothing. All of these other wires can be spitting out all kinds of crazy values. I don't care, because my regwrite and my memwrite are set to 0s. Since those are 0, nothing is happening in this area of the data path. The only interesting part of the jump instruction is happening up here in the instruction fetch unit. So before, when we looked at this picture, this was all we had. We could do PC plus 4, or we could do PC plus 4 plus this immediate that we got from the branch instruction added on to PC plus 4 in a special way. Excuse me. Now we need to do something radically different from the branch instruction. We need to take this 26-bit address, part of an address that we have. We need to extend it by 2 bits. We need to add on the top 4 bits of PC. Right? So we need to modify this to account for jumps. So now we're going to have to add a whole bunch of more stuff. We're going to have to add a mux. We're going to have to add this 2-bit extender. We're going to have to be able to bring in these top 4 bits of the PC. So that's what this chunk of the circuitry does right now. So let me walk you through that. Here we have this wire going back to the branch instruction circuitry so that we can do PC plus 4. On its way there, we grab 4 of those bits. So this was originally a 32-bit bus. We grabbed 4 of those wires, the values on those 4 wires, and we copy them so that they come over here as well to this little piece of circuitry. And those are just the 4 most significant bits of the PC. And then we bring in the 26 bits that the J-type specifies, the target address, the jump address right here, the 26 bits, and we append on the 2 zeros. This circuit, this box, essentially what it does is it calculates the full value of the new PC. And now we need to be able to choose between this new value of PC or whatever this circuitry does. Right? So essentially what we've done is we've said we're not going to disturb any of this. We're going to leave it be. So this NPC mux select value, which was the AND of the NPC select, the old NPC select, and whether or not the comparison was equal, we still bring it into this mux, and we just add another mux here to choose between the value that this circuit gives us and the value that this circuit gives us. So this mux, really what it's controlled by is whether or not we have a jump instruction. So this is going to have to be a new control signal, which is a 0 when it's any instruction except a jump, and a 1 when we're dealing with a jump instruction. If we're dealing with a jump instruction, what does NPC mux select need to be? Does it need to be 0? Doesn't matter. I don't care. This mux right here, if it's a jump instruction, is going to choose the value that this circuit gives me. So I don't actually care what NPC mux select is. Just as before when we looked at the entire data path, and we didn't care about regdest, xstop, ALU source, any of these things. Similarly, here, since we're not going to be looking at this value anyway, I don't care what NPC mux select is. I'm just going to let it be whatever turns out to be most convenient for me to build in my control logic. Really all I care about is that this jump is a 1 and I get this jump address. Any questions so far? No. Okay. Here's a little piece of news. The Tile MX100 just came out, and this has 164-bit ARM cores on one chip. Sort of a cool thing. It's a gigantic CPU. Dual issue in order. We'll sort of learn what those words mean in the coming few lectures. Basically, this is a behemoth of a machine, right? 164-bit ARM cores on just one single chip. Kind of cool. I wish I could tell you more, but Professor Chrissy knows more. Maybe he'll tell you when he's back. But that's all I got for you for now. Okay. Now we're looking at the full data path that we've built up all lecture long. So take a look at this. Let's bask in it for a few moments. We have all the registers in here that we need to be able to execute all the instructions we've talked about today. And this shows you this control, this blue control bubble. This will contain all the and, or, and not logic that is able to give us each of these control values. And then each of these control values are able to go to different parts of this circuit and choose different values. And notice that most of these values are going to muxes. And even the ones that aren't directly going into a mux are essentially a mux. The ALU is really just a mux, right? That chooses between different output choices, between input A and input B, or input A plus input B. There are a whole bunch of different choices for the output and chooses one. So really the mux is just, ALU is just a whole big mux. So it turns out this control is just going to be connected to every single mux that you see in this data path. Any questions? Yeah. Excuse me. Where did the shamt go? The shamt, so this is able to handle all the instructions that we talked about today. We haven't talked about the shift instruction today, so this doesn't contain any way for us to deal with the shamt. But hopefully, following sort of the process that we did today, where we looked at each component that we need in the data path and each choice that we had in the data path, introducing control signals, hopefully you'd be able to figure out where you'd need to introduce things to be able to deal with the shift instructions. Yeah? Okay, so the question was, should we try to understand this picture or the instruction from earlier on in the lecture. If you understand either one of them, you should be able to understand the other one. They're just sort of slight differences in how it's drawn, but they show exactly the same idea. This uses sort of slightly different notation on how it specifies what's on each wire and how each of these things are drawn, but they show exactly the same picture. Any other questions? Nope. Okay. So, here's a summary of all the control signals that we looked at. For add, we saw that these are the values of ALU source, control, regdest, regwrite, and PC select. For sub, for ORI, for load word, for store word, and BEQ. We went through each of these different values, right? And what I can do is I can take a look at this, and as I said, right, what I can do based on looking at this is basically come up with a big truth table. So that's what we'll do. We create a truth table out of this. Sort of like a truth table, right? So we have each of the control signals listed on the left column. And on the top column, we have, on the left, we have each of the rows labeled with the control signal. On the top, we have each of the columns specifying a particular instruction. And each of the cells tell you what value each of those control signals need to be for all of the different signals. So we see that to figure out what value these are going to be, all we need to do is look at the opcode for add, for ORI, load word, store word, BEQ, and jump. All we need to do is look at the opcode. That's all the information we need in order to be able to fill in this part of the table. To fill in these first two columns, we also need the funct, because we're looking at R types. For these guys, we don't care what the funct is, right? But as long as I know the opcode, I can fill in this entire table. So as long as I have the opcode in my control, I can determine each of these values. So if I were to write this out even more explicitly, I can take a look, for instance, at, let's take a look at regdest, right? Regdest is a 1 when we're dealing with an add, or we're dealing with a sub. And it's 0 elsewhere. We don't really care what it's here, so we'll just say it's 0. So if I write this out as a Boolean expression, what I get is that regdest equals add or sub. Similarly, for ALU source, here I see it's going to be ORI or load word or store word. So if we go back here, ALU source was a 1 for ORI, for load word, and store word, and a 0 or don't care elsewhere. So that's what ALU source is here. We can write this out for all of these different control signals, right? And I talked about this before, ALU control. We've been calling ALU control, we've just been sort of labeling what ALU operation we want to do in ALU control. We've just been saying add or subtract or things like that. We can sort of somewhat arbitrarily assign binary encodings to each of those names. So that's what we've done here, where 0, 0 is add, 0, 1 is sub, and 1, 0 is or. So we can break up ALU control into 2 bits. The most significant bit is a 1 when we're dealing with an or. The least significant bit is a 1 when we're dealing with a sub or a branch. Otherwise, it's 0. Once we have each of these Boolean expressions, I know that each of these are specified by these Boolean sub-expressions. To figure out whether I have a load word or not, I just need to look at the opcode bits. The most significant opcode bit needs to be a 1. The fourth one needs to be a 0. Third one needs to be a 0. Second one needs to be a 0. And the first and 0th bits need to be a 1. If I write this out, then I get load word. Right? And to turn this into a circuit, How do I turn this into a circuit? What gates do I need to turn this into a circuit? Just this bottom portion. What gates do I need to be able to give you a signal that tells you you're dealing with an R type, or you're dealing with a load word or store word? An AND gate and a NOT gate. Right? If I just have access to each of these bits, which I do, if I look at this picture here, I'm getting the entire instruction, the entire opcode coming into control. These top 6 bits are coming into the control. I have access to each of these opcode bits. Since I have access to each of those bits, I can just combine them with NOT gates and AND gates to figure out which instructions I have. So if I have a signal for telling me whether or not I'm dealing with a particular instruction, what gates do I need to combine those signals to tell me the value of each of these signals, control signals? Just an OR gate. I just need OR gates to combine each of these signals to give me the final control signals. So, turns out that control box, to answer the question of how do we set these control signals, we need some AND logic, and we need some OR logic. And that gives us the final output of each of these control signals. The AND logic will tell us exactly which instruction we're dealing with. The AND logic also has some NOT gates, right? But we have those AND gates in there and NOT gates. That will tell us which instruction we're dealing with. And by ORing, whenever we have these instructions, we can figure out the final value of these control signals. Are there any questions about that? I sort of skimmed through this table pretty quickly, but what I would suggest and recommend is to go through this table and see if you can write out each of these Boolean expressions. All I'm doing here to write this out is say, okay, for instance, memWrite is a 1 when I'm dealing with a store word. So memWrite is going to be just a store word. Xstop, I don't care here, I don't care here, it's a 0 here. It's a 1 here for when I'm doing a load word, or it's a 1 when I'm dealing with a store word. Otherwise, I don't care. So Xstop is load word or store word. Right? So that's how I came up with this OR logic. To come up with this AND logic, all I did is look at these bits and see where they were 1s, and combine these bits with AND logic to tell me whether I'm dealing with an ORI or a load word or a store word, and so on. Once I have all of those, going the wrong way, I can combine them in just this manner to make the entire control logic. Yeah?
Why do the Boolean expressions not differentiate between a has to be 0 and a you don't care? They just seem to show it either neither or completely.
Okay, so the question was, in the case where we have these don't cares, why aren't we doing anything with that here in this Boolean logic? What this Boolean logic is just saying is that regdest is a 1 only when add is a 1 or sub is a 1.
But the other stuff has to be 0, and I feel like that doesn't specify that those have to be 0.
Okay, so the way to convince yourself that this works is just to plug in all possible values. Right? See, if add and sub are both 0, what is regdest going to be? 0 or 0 is a 0, right? So when it's neither add nor sub, which means it's one of the other guys, my output is going to be a 0. If either one of these is a 1, regdest is going to be a 1, and add and sub will work correctly.
Add, sub, and ORI, and I feel like that shouldn't work, but then that would say it does work.
Add, sub, and ORI. Why don't you come down and we can talk about it after. That is all I have for today. Here's the final summary. We were looking at the single cycle processor. We went through these 5 steps, and today we finished off that red box for the of the data path, and we rounded out our topic of the control. Have a good week, and we'll see you all on Thursday.